Hello everyone, my name is Dawar Khan, and in this lecture we will talk about caches, especially with two types of caches, so data cache and instruction cache. We will also talk about locality of reference. So this is the agenda of the lecture. We will talk about memory hierarchy, then we will talk about locality of reference, and then cache memory in these two types. Finally, we will calculate the performance metrics AMAT for unified or this data and instruction caches, and then we will conclude with this summary of comparing these both types of caches. So this is the memory hierarchy diagram. You can see on the top we have registers and caches, then we have memory, main memory, and then we have secondary storage. If you go from top to bottom, the cost minimizes and the size increases. If you go on other hand from bottom to top, the speed increases and the cost also increases, but the size decreases. So here you can see this cache and register with main memory. These are called inboard memory, and next level is outboard memories and offline memories. Locality of reference is an important topic related to cache. It refers to the method of accessing next data or instruction in a predictable manner. It helps us to bring data from the RAM to cache or to keep data in the cache for the next use in the near future or the next few intervals of time. There are two types of locality of references. One is temporal locality, which means the tendency of a program to access the same data and instruction again in the next few intervals of time. What does it mean? For example, the CPU accesses data D1 in time T1. After some time, it's highly probable that the CPU will access the same data again. This is called temporal locality. Another one is spatial locality, which means the tendency of program to access the nearby memory location again in the next few intervals of time. Which means that, for example, in a time t1, the processor accesses location L1. It is highly probable that in the time t1 plus delta t, the processor will access the next nearby location L1 plus delta L, like arrays in our programming. In summary, we have like temporal locality to access the same location multiple times, and spatial locality is to access nearby locations again in the next interval of time. Example for the temporal locality includes variables, function calls, and frequently used data, whereas for the spatial locality as the iterations through arrays and nearby instructions. Benefits for the temporal locality because the data remains in cache, reducing the memory access time. For temporal locality, we need, for example, I access data D1, we have to put it in the cache for the use in the next few intervals of time. For implementation of the spatial locality, we bring a big chunk of data from the main memory to cache, because if I access this location in the next interval, it's highly expected that the processor will ask me the nearby location. What the cache is. So the definition of the cache is, this is a buffer or the fast memory located in between the CPU and the main memory. On the abstract level, we can call it a single cache, but in reality, in modern computers, we have multiple levels of cache. It's called L1 cache, L2 cache, and L3 cache. So if you go in this direction, the size increases, the cost decreases, the speed also decreases. But L1 cache is the fastest, this is faster, and this is less faster, the L3 cache. So in the one Newman architecture, we usually have this L3 cache, shared cache. This is an example of multi-core system, but the L2 and L1 cache are usually separate for each core. This is an example of unified cache in the one Newman architecture, where for each core we have a unified L1 cache, which is responsible for handling both data and instructions. But with the latest Harvard architecture, we have the L1 cache in two different types. So one is instruction cache and one is data cache. We have separate caches for both data and instructions. Why we need this? Because the CPU needs both instruction and data parallel. So to improve the efficiency, especially with the high performance and parallel computing, we need this two types of caches. This is called Harvard architecture. Instruction cache is responsible for storing and decoding frequently accessed instructions to improve the performance. The key features of the instruction cache include: it reduces fetch time, helps prefetch and pipeline the execution, and another key feature is it is read only. We cannot write except some exceptionals, but usually is read only, and this designed for the fast access. A working mechanism is similar, like general working mechanism of general cache. When CPU asks for some instructions from the RAM, the I cache first checks it in the I cache, and if it is found in the I cache, it is given to the CPU. It's called cache hit. But if the instruction doesn't exist in the cache, the I cache loads it from the main memory, and it is stored in the cache for the future use. This is called, like as we discussed in the temporal locality, this newly loaded instruction is stored in the cache because it's highly probable that it will be demanded in the next few interval of time, and so these are stored in the cache for the future use. There are some challenges which needs optimization techniques to handle these challenges. So the first challenge is cache misuse, which cause stalls in the pipeline. So in the cache hit, the idea is clear. We don't need any issue. There is no issue because the data is automatically fetched from the cache. But in case the cache miss, if the CPU requested instruction doesn't exist in the cache, it must be fetched from the main memory, which is much slower and halts the CPU pipeline, causing stalls in reducing performance. Another one is branch misprediction to unused prefetched instruction. Modern CPU branches predicts to guess outcomes like in the conditional branches such as if conditions or loops statements. The modern processor predicts the next outcome. But in case if this prediction goes wrong, the CPU discards all the pre-fetch instruction and reloads it with the accurate one. So this is another problem which needs optimization for the I caches. The last one is the SMC, which means simplified modifying code. This is a rare but important programming technique where the program wants to update the instruction inside the memory. So self-modifying code requires cache flush, which is invalidation, to force the CPU reload the updated instruction from the RAM. This is another key challenge with the iCache. Similarly, dcache, as the name suggests, data cache stores the frequently accessed data to speed up the memory operation. The key feature is it stores the data, which is in the form of variables, arrays, and stack data. And another key feature is it supports both read and write. It is usually larger in size than iCache, so it's a little slower than iCache. And for the writing policy, we need to follow the writing policies such as the write through and write back policies. Working mechanism again same as somehow with the iCache or general cache. CPU requests the data, dcache checks if it exists here in the cache, so it's called cache hit, and the data is given to the CPU. But in case if the cache miss occurs, data is fetched from the RAM and stored in the cache for future use. In the modified cache, if we have modification, this is also written back into the RAM based on the write policies, which include like write through, write back, and other writing policies. So this is the overall mechanism for the decache. So these are challenges in the decaches. The cache coherence, which maintains data consistency. Consistency means, for example, we have two copies of the same data and we make a modify here, so the other copy is outdated and we need to keep updated both of the copy consistently. So in multi-core processors, we have separate cache for each core. For example, in the previous slide we have shown here. So each core has its own private cache. So when one core modifies its data, for example, this data is modified, the data in other caches becomes outdated. So this causes data inconsistency, and we need synchronization mechanisms which needs extra CPU time. So this is a challenge, and it also this synchronizations and sharing up these updates takes memory bandwidth, so which slows down the efficiency. Another one is the cache evictions, which means that if we bring new data to the cache, since the cache size is very smaller, so we have to remove the existing data from the cache. So this is another problem, which data we have to replace with the new data. To handle this issue, we need some heuristic replacement strategies to improve the efficiency and handle this issue. Another one is the false sharing. When multiple cores access different locations, different variables within the same cache lines, even in if cores access separate variables, they still invalidate each other's cache lines due to the cache coherence rules. This causes unnecessary cache updates even there is no actual data sharing occur. But it's predicted that data sharing occurs, so it's called false sharing. So we need also another optimization for handling this issue. Average memory access time measure the effectiveness of memory access considering cache hits and misses. Usually we have this formula: hit time plus miss rate multiplied by miss penalty. So this is used for the average memory access time. In case of hardware architecture with different caches for instruction and data, the AMT total AMT is AMT for I cache and IMT for D cache. So here is the formula: instruction access time hit ratio multiplied by hit time plus miss ratio multiplied by miss time plus miss penalty. Again same for the data cache. Here are the two formulas. Here is an example number 1 where the access time is 1 and we have the memory access time 100 cycles. I cache miss ratio is 1%, which is equal to 0.01, and D cache miss ratio is 5%, which is equal to 0.05, and we have 33% of data or instruction loaded stored, which is equal to 0.33. So for instruction cache we have AMT equal to 100% multiplied by 99% cross 1, this one, plus 1% cross 1 plus 100. This is the one is miss time and miss penalty. So if you calculate this, it gives us 2 cycles. For data cache we have this 33% and 95% multiplied by 1 plus 5% multiplied by 1 plus 100. It leads us to 2 cycles. So the total AMT is 4 cycles. Here is example 2. We have instruction cache, 1 cycle hit time, miss rate is 4%, miss penalty is 50, and access is 40% for the instruction and 60% for instruction and 40% for the data. So for the instruction cache we have 0.6 plus 1 plus 0.4 multiplied by 50, which gives us 1.8 cycles. For the data cache we have 0.40 from 40%, 2 from here, 6%, which is equal to 0.6 multiplied by 50. So it gives us 2 cycles, and if we accumulate, this gives us 3.8 cycles. Here is another example with the miss time plus this is included another extension as a miss time. So you can see this 0.6, 1 is the head time, 0.04 is the miss rate, and 10 plus 50, these two things, miss time plus miss penalty. So if we calculate this, it gives us 2.04 for the instruction. Similarly 0.40 for the data cache, and this 2 is the head time, 0.6 is the miss rate, and 12 plus 50, these are the miss time and miss penalty. So the cumulative value is 2.288 for the data, and if we add these both, it gives us 4.328 cycles. This is the total AMAT. In summary, we need in the hardware architecture we have separate L1 caches, which is instruction cache and D cache. Why we need this? Because we need in the modern parallel computing we need both data and instruction in the same time. So these are much efficient as compared to the unified cache of the one Neumann architecture. And what are the key difference between these two types of caches? It stores instruction, the another one stores data. It is a read only. We cannot write in the instruction cache, while the data cache supports reading and writing. And for writing, we have this writing strategies: write through, write back, and others for the distributed computing. Usually, both of them are in the same level, L1 caches, but instruction cache is smaller and the D cache is larger, so is a difference in the smaller. So instruction caches are faster, being smaller in size, and the latency is lower. And here the latency is a little higher because of its size. So there are different challenges, and for these challenges, the instruction cache has the optimization techniques of prefetching and branch predictions. If the branch prediction is not accurate, it gives an issues. Similarly, in data cache we have this inconsistency problem and false sharing, as well as the cache injection problem. So we need this writing policy right back, and we need multi-level caches to handle this data inconsistencies. Thank you. This was all about the lecture. Thank you.